The Sun's magnetic field is crucial to our solar system. The planets circling our Sun are swaddled in a sun-generated bubble called the heliosphere. Closer in, the Sun bombards Earth with a powerful stream of charged particles called the solar wind. And these particles can affect orbiting satellites and the planet's electrical grid. Telescopes, like the Solar Dynamics Observatory, are sharpening our picture of the Sun's outer atmosphere, known as the solar corona. It's the changing magnetic field in the corona that causes solar flares and eruptions, which hurl balls of plasma out into interplanetary space. The strings of plasma that you see here are called coronal loops. They're bright and easy to observe, so they can be used to trace some of the corona's magnetic field lines. But further out, plasma emission becomes dim and more diffuse. And, because spacecraft can't fly in close enough to directly measure it, the large-scale structure of the coronal magnetic field largely remains a mystery. For this reason, scientists were excited when Comet Lovejoy approached the Sun in December 2011. Lovejoy belongs to the Creutz's family of comets, often called sun-grazers because they periodically fly into the Sun and fizzle out in its atmosphere. But Lovejoy was so big, roughly 200 to 500 meters in diameter, that it was able to survive the Sun's corona and fly right out through the opposite side. At its closest, it passed within 140,000 kilometers of the Sun's surface. Lovejoy was recorded by a number of telescopes, including NASA's Solar Dynamics Observatory and twin stereo spacecraft. As we watched the comet approach the Sun, we noticed something bizarre. Its tail wiggled and rapidly changed direction. It didn't follow the predictable curve that most tails do, and we wondered why. A comet's tail is essentially a trail of vaporized ions, so we hypothesized that the wiggles we observed were the result of interactions between these ions and the Sun's magnetic field. Then, using a state-of-the-art computer model of the Sun's corona, we connected the motion of the tail directly to magnetic field lines, showing that Lovejoy was, in fact, probing the invisible magnetic field of the solar corona. Here you can see the magnetic field lines we used to extrapolate the motions of the comet's tail. Blue lines are closed loops, and orange lines extend out into space. Following Lovejoy has proven invaluable for physicists. The comet provided an opportunity to probe an area that our own spacecraft can't reach, and it did it in a new way, one that's complementary to other methods, like imaging the Sun's corona at varying wavelengths of light. We look forward to the next sun-grazing comet, because the more we know about the solar corona, the better equipped we'll be to interpret the Sun's activity and even predict how it will affect the Earth.